Hey, what's up everybody, and welcome back again. And now we're going to extend our knowledge in balancing equations and writing equations with ionic equations. Now, what exactly are ionic equations? Well, when you have a displacement reaction, whether it's a single displacement or a double displacement reaction, you would look at the products that's made, all right? For our case, the products that's made. Now, when one of your products or reactants involves aqueous or solutions, that means when you put those substances in and it becomes ions in solution, you have an aqueous or solution, okay? So, for example, HCl is hydrogen chloride, and this is a gas. When you put it in water, what will happen is that it will turn into hydrochloric acid, which is an acid. And in acid, these substances in hydrochloric acid will further break down into hydrogen ions and chloride ions. Okay? So this is what an aqueous solution is. And it also applies to salt. Like, for example, salt, NaCl, all right, it's a solid crystal. You can buy that in a marketplace. You put it in water, and it becomes an aqueous solution. That means the salt will break apart or dissociate to become sodium ions and chloride. Okay? So that is an aqueous solution for both of these circumstances. Great. And now, because of that, and when you do conduct reactions involving aqueous solutions, your products that you make could either become a gas, it could either become a liquid, or become a solid or a precipitate. And your teacher should kind of go a little bit into that with you guys. In this particular show, we're just going to briefly describe some of these ionic equations and write the equations for that. So before we begin, let me ask you a question. What is the purpose of writing ionic equations? Well, if you look at a reaction, an equation like this, for example, it may be a little difficult to determine which of these substances within the reactants actually underwent chemical change during the course of the reaction. Because not everything in here will undergo change. Some of it will just remain as so. And so, in order to really narrow down which of these substances in the reactors underwent chemical change, and if it involves aqueous solutions, we use this concept called ionic equations to just kind of throw away all the noise, all the mess, and focus down right onto those specific substances that underwent chemical change. So here we have a classic example. Hydrochloric acid mixed with sodium hydroxide. These two mixed together in solutions form your aqueous salt and water. Great. Now, in this equation, which of these substances underwent change? But before you write the ionic equation, you have to know that one of the substances must be a gas, liquid, or a precipitate, a solid. And in this case, we have water that's formed that is a liquid. So we can now really write the ionic equations. So for writing ionic equations, every time you see the state symbol aqueous, you will break it down into its two respective components. So for that case, I would just draw an arrow to represent what it broke down into. Now liquid here, this liquid, the water liquid here, the water molecule, does not break down. It remains in covalent bond, and so it does not dissociate or ionize. All right, looking at hydrochloric acid in water, hydrochloric acid will ionize, completely ionize into hydrogen, and I'm writing this down like that, and chloride. Okay? And note that I still continue to write the state symbols as I broke these substances up to its respective ions. Sodium will be formed, so sodium has a plus charge. You should know your charges by now, folks. And hydroxide will be a OH minus. Remember, hydroxide is not a HO, it's an O. Anyway, and it will form sodium ions with chloride ions. Alright? So all these three substances broke apart because these substances are in aqueous solutions. Water, on the other hand, did not break up, so it will remain as soap. And immediately what you noticed is that there are some substances that on the left side of the equation are repeated again on the right side of the equation. And so in this example, we have chloride that's exactly the same and sodium that's exactly the same, so we cancel them out. These substances here are called spectator ions. They are called spectator ions because, like in a tennis match, me being the spectator, I'll just look at the game that's being played, but I'm not the one playing the game. Okay? So when you cancel them out, the remainder will be your ionic equations. So what did not cancel out? Well, the hydrogen ion did not cancel out, and the hydroxide ion did not cancel out. And, of course, the water molecule that's formed did not dissociate or ionize. So rewrite it back like so. So in this whole entire reaction, we have isolated and removed the spectator ions. And what we're left with are the actual ions that underwent chemical change. So hydrogen ion plus hydroxide ions, when these two ions collide in the solution, boom, it forms water molecules, and the water molecules just remain in the solution like so. Great. Next example. We have another displacement reaction, this time involving magnesium metal, maybe a magnesium ribbon. You cut it up in little pieces, put it in a strong acid bath, a strong acid solution, and boom, you make an aqueous magnesium chloride solution, and you got a hydrogen gas that's formed. So again, when we write the Ionic equations, we got to split up whatever is an aqueous. Oops, sorry, so this one can be deleted off. So hydrogen did not split up because it's not an aqueous. Magnesium did not break up, but hydrochloric broke up, and magnesium chloride also broke up because it's an aqueous. All right, let's write down the ions or substances that's formed. Magnesium did not break up, so I just copied it down. Hydrochloric acid broke down into hydrogen chloride, broke down into hydrogen ion and chloride. Okay? And the magnesium salt that's formed, right, is actually still soluble in water. So I write down the salt like that, and I form 2 chloride ions. Oh, I did not balance this. I should have done that. So there you go. Balance them up. Okay. And hydrogen gas that's formed. All right. Now looking at this equation, you will notice that it seems that chloride is on the left side of the equation as well as it is on the right side of the equation. So that must be my spectator ion. So cancel that. What I'm left with now is my ionic equation. So the magnesium underwent chemical change with the hydrogen ion to form the magnesium ion that's soluble in water, together with the, together with the hydrogen gas. Okay? So here is my net equation. Now let's do a final example. Okay? Let's do a final example, and I'm going to do another double displacement reaction that involves a precipitate that is formed. So zoom up with the camera. So let's say silver nitrate, which is aqueous in solution, reacts with, let's say, sodium chloride, which is also aqueous in solution, forming silver chloride and sodium nitrate. Okay? Sodium nitrate is aqueous in solution, and silver chloride is not. It actually is a solid. Now, the question is, when you have a reaction like that involving a lot of salts, all right, how do you know if the salts are soluble in water or not? Well, there is a table that you should refer to, or you can Google them, called the solubility rules. Okay, solubility rules. And you will Google that and refer to that set of rules to determine if the salts that you have are soluble in water or not. All right? And by looking at that, you can determine the physical state of all these salts. Now, I will publish the solubility rules maybe in the description or in the future lesson. Okay? But anyway, these are the physical states for this equation. So what happens is these things will break apart. Okay? Silver chloride stays the same, and sodium nitrate will break apart or ionize, or actually not ionize, dissociate, because they are salts. Okay? So silver ions gets formed with nitrate ions in solution with sodium ions, okay, and chloride ions. And what you form is silver chloride, which is a solid, plus sodium ions and your nitrate ions. Not enough space, so boom. Okay, immediately I've noticed in this equation is that nitrate and sodium are spectator ions because they're both the same on the left side of the equation as well as it is on the right side of the equation. And so what I'm left with is the aqueous silver ion combining with the chloride to form silver chloride. And here is my precipitate. So in this whole equation, the actual substances that underwent chemical change would be the collision of silver ion with the chloride, and when they collide, the attractive forces between the silver ion and the chloride is so strong that it will remain together and packed up and will accumulate instead of allowing the water to dissolve it. Right? So that is pretty amazing. If you have any other equations, whether it's regular chemical equations that require balancing or writing and balancing ionic equations, please leave it in the comments below, and if I get about 5 of them request, I will make a video just to clarify any of these equations you have. Alright, have a good one.